Okay, let us start today. 4.3. Maxima and Minima. So we did a lot from the pre-calculus, right? So we're gonna learn the calculus technique. So here, if we have like from calculus, how about, let me erase it this way. How about like that, okay? Let's say this is 2, -2, this is a 2. How about that? Okay. If we are looking at just the function, the graph, okay, where is the decreasing? How about increasing first? F is increasing. Which part is increasing? Yeah, from here to here is increasing, good, okay. So increasing. So it will be -2 to, oops, maybe we said 1 there, so 1, right? How about decreasing? So everything is a fancy. F is decreasing on where? So this part, right? This part is decreasing, and this part is decreasing, okay? So -infinity to -2, union of 1 to infinity, right? Okay, let me erase this one. All right, so let me write down the definition of I just want to understand where is decreasing and increasing. So definition, absolute maximum, absolute minimum. So let me write down F has an absolute maximum on interval SC if f of c is greater or equal to f of x for all x in the interval. Let me using I as interval. So TA, can you please answer him in the chat? Thank you. And F has an absolute minimum on I, which is interval, SC, if f of c is less than or equal to f of x for all x in I. Okay, and if there is absolute maximum and minimum at the same time, then we call it absolute extremum, right? Absolute maximum Absolute minimum. We say that absolute extremum. Okay, so absolute minimum, absolute maximum. Let me give it to you. Think. This one first. Think. Most, highest. Okay, and absolute minimum, most, lowest. No. So it can be tied, right? So earlier, oh, we don't have earlier one. Like this, right? So this is a tie. So there is the two absolute minimum, right? Absolute minimum. Both of them. Okay. So let me draw so we understand graphically. Okay, there's a arrow that means keep going infinity, keep going negative infinity, right? So is there absolute maximum or absolute minimum? What do you think? It cannot be positive infinity, it cannot be negative infinity, right? It must be in the interval, right?
I don't think it has an absolute maximum then.
Also, no absolute, let me denote it like this, or minimum. Okay, very good. All right, number two, if we have the graph looks like that, do you think is there absolute maximum or absolute minimum?
Absolute maximum.
Okay, good. Absolute maximum is on the top, right? So let me see. Yeah, max. Okay, good. She said neither to indirect message. Okay, this is absolute max. Number three. Okay, is there absolute max or absolute minimum?
There's both.
Both. So absolute maximum there. And as I said earlier, if the value is the same value, then there is also absolute minimum, right? At the same time. Okay. So even though we said the most highest, most lowest one, if there is the same value, there can be more than one absolute minimum or absolute maximum. Okay. Number four. So what do you think? Is there absolute maximum?
Yes.
Maximum is the right side, right? So because I draw differently. So this is the absolute maximum. How about minimum?
I think still,
So there is absolute minimum.
well, the point is undefined, but there's a point right before that point that maybe could count as the absolute minimum.
So we don't say this is absolute maximum because minimum, sorry about that. Absolute. Because the function is not the continuous, okay? And let me erase on the top. Okay, let me draw the first so you can take a look. Number 5. We have this. So what do you think? Is there absolute maximum and absolute minimum?
I think yes, but I could be wrong.
So absolute max,
Mhm.
absolute min, yes?
Yes.
Okay, good. That is it. How about this one, last one? So is there absolute maximum?
I would say absolute minimum.
Is minimum good? How about the minimum? I mean, maximum.
No, there's no maximum because it's
Because keep going, right?
keeps going.
All right, so look, we can, looking at this older graph, right? And then we can create extreme value theorem. Let me write down. So theorem 4.1, extreme value theorem. They say that if f is continuous function over the closed. Closed means we include the end point, right? Let me write down later. Closed and bounded. Bounded means somehow, let me write down this, like the here. It's bounded by here, bounded by there, okay? And bounded by here, okay? So basically there is no keep going positive infinity, keep going negative infinity, okay? So let me write down bounded later. Bounded interval AB because closed, right? Then there is a point in the interval AB. F has absolute maximum over AB. How about, let me make it shorter. Maximum and absolute minimum. Oops. Make it short. It's absolute maximum and absolute minimum. Over the closed interval A and B, right? So I said close means think Oops, blue color. Think include the endpoint and bounded. Think not keep line positive infinity nor negative infinity. All right. Okay, so in this case, which one is we can apply the extreme value theorem? Number 1, 2, 3, 4. Okay, how about this? Let me close here. Close, this means close. Which number we can apply it? Extreme value theorem?
Number 5.
Number 5, yes.
And number 4.
Number 4 is, look, that's not continuous. So
Only
Number
number
3.
5.
number 3, yes.
And yeah, that's it.
That's it, right? So can you see that? F is continuous function closed, right? Closed means we don't have an error, right? So include the endpoint. So number 3 and number 5 close, right? Then bounded. So I make the line bounded by above, bounded above, bounded below, right? Okay, here actually there is an asymptote as well, looks like, right? So number 2, but then that's not closed, number 2, okay? So this is closed, bounded, oops, too close. I don't want to waste time for this one. Okay, so maybe we can draw like that. Bounded above. This is bounded below. Okay. Continuous. That's the basic the condition satisfied. Okay. Continuous, closed, and bounded. Then there is absolute maximum and also absolute minimum. Can you see that? They both occur in the graph. Okay. Number 2 is not because not closed. That's why only absolute maximum in this case, not the both. Is it clear? That is extreme value theorem. Let me erase. All right. Then look this one. We have another definition from the pre-calculus. So this is local maximum. Local, let me just write down local maximum and local minimum. Minimum. So both of them we call the local extremum. Okay. So we call this as a local maximum. Okay, and we called number 1, number 2. Let's see. This is also local max. How about this? Is it local max minimum?
Local minimum.
What this come from? Local minimum. Okay. How about this? Number 4. How about this? Is there local minimum or maximum?
Neither.
Neither. So no local extreme. Okay. Let's see. Okay, how about this one? Let's see. How about this one?
Is it like a little curve on the top?
So anyway, this is a arrow, right? So it does not matter.
Oh, okay. There's a
No.
local maximum, or
Because arrow there, so
okay.
no local extrema. Okay. So yeah, the local max, local min, we can think about the absolute max, absolute minimum, right? Okay. If there is most highest, if there is most lowest, right? Okay. 2 and 3 closed? I don't think closed. Okay. And how about this?
Yes, there is a local max and min.
Yeah, this is the local max. And let me write down. This is the local minimum. So I don't have to write down definition, right? Okay. Which one has absolute max or minimum in this case?
One and 6.
1, 6, 6 cannot because keep going on the top, keep going
okay.
negative infinity, right?
Oh, then 3. No, not 3. Well,
Hold
three
on
will
one
have a,
second. Someone said something. So this one, we can say that absolute max. And then there's two.
two,
Yes. Uh-huh.
and 3 has a absolute minimum.
Yeah, absolute minimum. Good. Excellent. So you guys understand what's the differences between local max, local min, okay, and then absolute maximum, absolute minimum. Very good. All right. Then look. What is the slope at this point?
Zero.
0. So f prime over c equal to 0, right? And what about, no, we cannot do that because this is corner. How about this one? Oops. What about slope?
Same thing, 0.
0, good. Okay. How about here? What's the slope? F prime over C2, right? So we express the slope as a derivative, right? We know that. That's why I'm using that, the notation F prime over C, right? Then F prime over C2, C sub 2, we get 0 as well, right? Okay. Now, this is the slope is the 0, right? We say that 0 slope. Okay. Does anyone remember this one and this one? And this is to consider f of c equal to 0. And this one, does anyone remember of this one from the previous? This is a we cannot derivative at the point. Undefined, yes, good. So we said f prime is undefined, okay? Because we learned that f, I hope your classmate is not picking on the spell here. Because we learned we cannot derivative if there is corner like that, corner. This is also corner, okay? And we cannot derivative vertical tangent line. Okay, so we say that graphically, we cannot derivative at corner and vertical tangent line, then we say that f prime of c undefined. Spell. Okay, and this is also f prime of c undefined. Okay, all right. Then remember this, the first one, the fourth one, and sixth one, we get f prime over c equal to 0, right? But then number 1, number 6 has local maximum and local minimum for the number 6, right? But number 4, we don't have any local extrema, right? And number 2, number 3, number 5, f prime of c is undefined. Means that we cannot derivative at the point, right? Undefined does not exist, right? But then number 2 has a local max, and number 3 local minimum. But number 5 has no local extrema. Can you see that? Okay. So we're gonna learn this one. Hold on, let me erase this one. Okay. Critical point definition. Definition. It's about, let's see, beyond the point in the domain of f, we say C is a critical point of f if f prime of c equal to 0 or f prime of c equal to undefined. Okay. All right. Then what is it telling us? Critical points. Okay. So critical points when f prime equal to c equal to 0 or f prime of c equal to undefined, that is critical point for the c. Okay. But what is it telling us? By theorem 4.2, formats theorem. If f has a local extremum, okay, then that means local maximum or local minimum as c I don't know. SC and F. I need to fix this one. He's gonna talk to me again. F is differentiable. Scrubber everywhere. SC, then f prime of c equal to 0. All right. So we had local max, local max, local min, right? Then look, if f has a local extremum at c, this is c1, c2, c3. How about that, right? Then everything is 0, right? But then looking at the definition, we have a critical point, f prime of c equal to 0, or f prime of c equal to undefined. It can be, this one is telling us, it can be there is a local extremum or not, right? Because we saw the bunch of example from 1 to 6. Can be or cannot be local extremum. Okay? But the other way, if f has local extremum as c, then and f is differentiable as c, then must be f prime of c equal to 0. Because we know this is c1 equal to 0. Because the horizontal tangent line, right? Make sense? All right, so then let us find the critical points graphically. I mean the algebraically. Let me erase this one. X squared plus 4x. Okay, so critical points, we're gonna find the f prime of c equal to 0, right? Okay. Let us find f prime of x. What do you get? F prime of x? You're busy with the writing, huh? With derivative, what do you get?
X squared minus 5x plus 4.
Okay, then set this one equal to 0. Then solve for x. That's the c, okay? So solve for x. Then can you please factor out this one? Is it factorable? What do you get?
X minus 1, x minus 4.
Thank you. Then we know that this is equal to 0, this is equal to 0. So this is 1, this is 4, right? Okay, so this graph is like this. Let me draw. So this is 1, this is 4. Okay, look. This is a local max. And this is a local minimum. Okay? Good. Let us do other one. Let me erase. How about this one? So we're gonna find the critical numbers, critical points. So let's set it up. Derivative, what do you get? F of prime of x.
Use the quotient rule.
Quotient rule, excellent. So this is f over g, f prime g minus fg prime over g squared. So then f prime, what do you get? It's 4. And g, which is 1 plus x squared minus f and g prime.
4x times 2x. Or
4x. And all over g squared, which is 1 plus x squared, then squared, quantity squared, right? Let us simplify 4 plus 4x squared minus 8x squared. Can you please calculate the numerator? So what do you get? So 4x
X
is negative. Thank you. All right. So we know that we can find the critical point, which is f prime of c equal to 0. F prime of c is undefined. Okay. This is f prime. Okay. So look, numerator set equal to 0, then there is f prime of c equal to 0. Make sense? And we set denominator equal to 0, then there will be the f prime is undefined. Make sense? Is it clear?
Could you repeat that one more time?
Okay, let me write down. F prime of c equal to 0, that's the numerator. Okay, in this case, f prime of x equal to 0, right? Then solve for x. Now we have two conditions in order to have critical point. One is f prime of c equal to 0. Second one, f prime of c is undefined. Remember? Okay. So like a fraction, when we say they're undefined, the denominator equal to 0 is undefined, right? Same as here. We say that f prime is undefined when denominator equal to 0. Make sense? Is okay? Yes or no? For critical numbers, critical points.
Yes.
Yes, okay. But then let us talk about the f prime of c undefined. 1 plus x squared, and then we get squared, right? Then this is always positive. I mean, we never get the 0. Never get 0. It's hard to write. Never get 0. Since okay. Now we're gonna find just the x. How? What do you get for x in this case? I'm going to number 1.
I got 1.
You got 1. Okay, so we have 4, and then we move to the negative 4x squared, right? All right, then 1 equal to x squared. When we square root both sides, it's x equal to plus minus 1. Is okay?
Yeah, thank you.
Yeah, that's critical point. All right, then.
A quick question. So when we're doing this, if there's something in the denominator, are we always going to consider that undefined? Is that what you're saying?
That's correct. It's
Okay.
like we need to find the we need to look for the vertical asymptote. Then we set x the denominator equal to 0, right?
Oh, that's right. Yeah.
Yeah.
always
But
be
then
an
in this case,
asymptote.
it's not the original function. This is f prime, right?
Okay, yeah, so it's not necessarily an asymptote, but it's always undefined, whatever's in the denominator. Okay.
In this case, f prime, right? But when we talk about the vertical asymptote, it's original one.
That makes sense.
Right? So f is undefined. This is f prime is undefined. Can you see that?
Yeah.
Okay. All right. So this is the graph. Looks like that. Ooh, I don't know how to graph. This is like this. So smooth, little bit smooth. So you don't consider this as a corner. So this is a local minimum. And then this is the local maximum. Okay? All right, let me erase this one. We have another theorem. Then we do that. And we're gonna use this one for next section. Clear all. Theorem 4.3 location of absolute extrema. That f be continuous function over a closed and bounded interval by the absolute maximum over f over I and the absolute minimum over f over I means interval, okay, must occur at endpoints of I at critical points of f in the interval I, okay? All right, so let us do example. I'm gonna show you how to do it. Find absolute maximum and absolute minimum of f of x equal to negative x squared plus 3x minus 2 over 1, 3, 1, 2, 3. Okay? All right, so we're gonna find critical value. Okay. So f of prime of x, what do you get? Critical points, CP. So what do you get this one?
Negative 2x plus 3.
Okay, now we set this is equal to 0 and start for x. What do you get? What's absolute? This absolute. So absolute, right? This absolute too. Every absolute, I made a mistake. Okay, so what do you get? Let me fix the absolute, and then you find the S. How about that? Man, English class. Okay, so what do you get this one, X?
3/2.
X equal to 3/2. All right, now this is step one. Step two, we evaluate the endpoints and the critical points, okay? So f of 1, we plug in. That is a negative 1 squared plus 3, 1 minus 2. What do you get? F of 3 equal to negative 3 squared plus 3 times 3 minus 2. What do you get? F of 3/2 equal to negative 3/2 squared plus 3 times 3/2 minus 2. What do you get? I need your help. So what do you get? F of 1?
I
0.
think that's 0.
0, thank you. F of 3?
-2.
Negative 2? Thank you. F of 3/2?
It's 1/4.
1/4, okay. Then we're looking at the value, right? So which one is the smallest one, most smallest one, most lowest one? This one, right? So we call this as absolute minimum. And which one is the most largest value, which is a positive 1/4, right? So we call this is absolute maximum. Okay, makes sense? Is it clear? So if we, okay, good. If we draw the, this one, so it's like that, it's close. So ending is close, right? Then here is, this point is absolute maximum, which is 3/2 and 1/4. And then this is also absolute minimum. It's 3 and -2. Okay, make sense? Question? Okay, let me erase this one. All right, let us do quick example 2 application, okay? So a company that produced cell phones has a cost function of C equal to, so basically C over X, right? equal to x squared minus 1200x plus 36,400, where C is cost in dollars and X is number of cell phones produced in thousands. How many units? Come up here, fix, please. Of cell phones. Oh, yeah, here, I got it. Because I writing so fast and then they cannot catch that. How many units of cell phone? Minimize this cost function. Okay, come here, fixed. Okay, so we have C prime of C of x, then we're gonna find C prime of x, okay? So what do you get?
2x minus 1200.
So 2x minus 400, 1200, sorry, okay? Then we set this is equal to 0. Then solve for x. What do you get this one?
$600.
600, right? Because this one looks like that. I'm not sure, but. Okay, so 600. So x for the cost function. And then this is cell phone, number of a cell phone. Okay, if there is 600 units, then they do minimize this cost function. Okay. All right, let me erase this one. A ball is thrown into the air and its position is given by h of t equal to negative 4.9 t squared plus 60t plus 5. And then this unit is meters. Okay, find the height at which the ball stops ascending how long after it's drawn does this happen? So this is like that, right? Parabola downwards. So we are looking for the HA prime of T. Oh, I did not set equal to 0 earlier. I was rushing, sorry. Okay, f of prime over T, we're gonna find, what do we get? So you should use a calculator, right? Because that's
Negative 9.8 t plus 60.
negative 9.8 T plus 60. Okay, set. Negative 9.8 T plus 60 equal to 0. Solve for T. What do you get?
6.12245.
6.2. Okay, then let us do that. H of this is a time 6.2. There's no timer. They don't mention anything about the time per second. Interesting. So since this is the height in terms of a function, in terms of a time, right? So we're gonna plug in 6.2 there. Maybe 4.9. So let's just a second because normally we do that, right? T 6.2 squared plus 60. Can you please calculate this one? So what do you get this one?
Uh, 860.356.
Meters. Oh,
I'm sorry, I didn't put the negative in.
it's negative?
Yeah, I got the wrong answer, sorry.
Okay, some people got the 188.64. So which one is correct?
Yeah, I'm pretty sure it's 188.64.
188, okay.
Yeah.
So it's a negative?
No, it's positive.
It's a positive, right? Okay. Let me erase. I'm gonna erase.